appreciate that. I appreciate everyone who's here. I know we're at a stressful time of year for everybody as APs for chemistry are popping up about 2 weeks from yesterday. And of course, I'm sure several of you have many other APs before chemistry or perhaps after chemistry. I know my students do too on top of that. Now, one of the things we're going to do today is we're going to look at several examples, and hopefully by the time we leave today, you'll have a good framework in your head that when a thermodynamics question comes up to ask about the thermodynamic favorability of reaction, you will have a nice checklist in your head on things you want to look at. Now, it is across the board, it's really important here that you work through some of the examples with me as we go through together, as they'll be on PowerPoint. I will give the PowerPoint to Mr. Akinpura after it's said and done, if you a PDF of it, if you'd like to rework some of these questions, but we're going to do those calculations during our time together. The other thing too is I encourage questions. So if one of you has a question directly, I have no problem with you just opening up and either asking it through the chat, or if you want to open up your microphone directly for a question, please feel free to do so. The whole goal of this is to make you feel comfortable, both with thermodynamics, which I'm going to be working with, and electrochemistry, which Dr. Gelder is going to be working with after I'm done from right there as well. So let me go ahead and get started. I'm going to share my screen. And let me share the entire screen and go to our PowerPoint and play it from the current slide. There we are. Okay. So what we're going to talk about today is we're going to talk about why reactions happen. Okay. And we're specifically going to look at delta H naught, delta S naught, and delta G naught. And I kind of call it a review in 4 equations because we're going to look at 4 different examples as we go through here across the board. And there's my name and my email address. Always feel free to contact me at any time. Mr. Akinpura has that information as well, although he is as valuable a resource as anyone when it comes to thermodynamics. He can answer any question better probably than I can in that regard as well. So let's go through and get started with in terms of thinking about why reactions. Okay. So here's the overview of what we're going to look at today. We're going to talk about some bond breaking and bond making, although that really kind of goes back to a previous unit in AP chemistry in unit 6. It's going to be important for what we're going to talk about here. We're going to spend a lot of time on the role of entropy and the second law of thermodynamics, look at examples, and then the last question, which is going to tie back to some earlier stuff in kinetics, is this reaction should happen. Why doesn't it? Okay, from right there too. So what I want to do is I want to look at a type of question that we would see on the free response of the AP chemistry exam. This could also be a multiple choice question, although it would just be written in a slightly different format, okay? And so here's what we want to be able to do by the end of our hour together. So right now we have the reaction of C2H2 with chlorine gas to make C2H2Cl2. That's ethine reacting with chlorine to make a molecule called dichloroethene. And it can be synthesized by the reaction of C2H2 and Cl2, as shown by the balanced chemical equation. You'll notice on the right-hand side here, if we look, we're given this expression, this delta S, okay, that's going on top of that right here, okay? And it's given a negative value, which we're going to talk about as well. And the first question that goes through here is they say, using particulate level reasoning, account for the fact that this delta S is negative. And then show on top of that. We'll talk about that a little bit later on as we go through our review. Then they give us some, it looks like thermodynamic information for heats of formation values. And then they want us to calculate the delta H naught of the reaction in units of kilojoules per mole of reaction. Okay, from right there. So now we have some thermodynamic data. We have delta S naught, we have delta H naught that are moving from right there too. And then after that, as we move forward, the important part of the question comes on the next slide. And that is 3 students, Paul, Linda, and Kim, are discussing about the thermodynamic favorability of the reaction. And so Linda claims that the reaction is never thermodynamically favorable at any temperature because the delta S naught, which we saw before, is negative. Paul claims that the reaction is thermodynamically favorable at all temperatures because the products are more stable than the reactants. And then Kim claims that the thermodynamic favorability depends upon the temperature. So we have 3 students who are discussing this. And ultimately, whose claim is correct and justify your answer. Now, I'm going to tell you right now, if you can address this sort of question, you're going to be in very good position to answer pretty much any question in terms of thermodynamic favorability and chemical reactions from right there too. So let's start kind of some aspects of that, and let's delve in to some aspects of these claims. So first of all, what does thermodynamically favorable mean? Okay, what's the idea for what thermodynamically favorable means? So I pulled a YouTube video. All right, if we deal with the thermodynamic favorability, and this is a reaction you probably have done either in your first year class or your AP chemistry class. In fact, Dr. Gelder, I think, would agree this reaction has some major implications for what he's going to talk about next hour. And this is the reaction of copper wire and silver nitrate. And notice all they did is they put the copper wire in a solution of silver nitrate, and right away you see the formation of this gray fuzz, which is silver metal, onto the copper itself. So this leads us to right away to really what we mean by thermodynamically favorable, which your teachers may have also used kind of in older language, the word spontaneous, although we don't love that word as much anymore as thermodynamically favorable. And what thermodynamically favorable actually means is the reaction is going to happen if you just mix the reactants together. Notice here, all the person did was put the copper wire in the solution of silver nitrate, and magically we have made some silver metal on the copper wire. And you can also see that the solution is turning a bluish color, which is an indication that copper ions are going into the solution from right there. So when we say thermodynamically favorable, what we're saying is that the reaction should happen if we just mix the reactants together. We shouldn't have to do anything. Shouldn't have to add in the energy or anything else. And the reaction should just occur on its own moving forward, okay? Now, let's go back for a minute to Paul's claim that said, what drives favorability? That's really what we want to play with from right here too. And remember that Paul made in his claim that any chemical reaction that is stable, that makes stable products, that if the products are more stable than the reactants, would be favorable. Well, what I want to show you here is I want to show you a simulation I put together last night using Coulomb's law. And I want you to see, for example, what I have here are two ions that are going to come together to make effectively an ionic bond. Or you could think of these as two particles that are about to make a covalent bond, where one has an excess of electrons and one has a deficit of electrons from right there too. So these two particles are clearly attracted to one another. But I want to show you something really interesting that happens, okay? Notice they're attracted to one another. When we start the video, they come together. And as they come together, they move faster and faster and faster. And they try and make a bond, but something interesting happens. The problem is that they're moving so quickly when they try to make the bond, okay? They just fly right apart. And there's no way that these two particles stay together, although clearly they're attracted to each other, okay? And they kind of want to make the bond. But as they get so close to one another, they just bounce off because they have so much speed that once again, they can't do anything about it. And we can just have this happen forever. And what this shows us is that when things are trying to bond for themselves, there's this speed we need to get rid of. We need to get these particles to slow down so that they can feel the attraction, all right? So that they can feel the attraction for one another, but not have so much velocity that they bounce off. So what I'm going to do is I'm going to do exactly the same reaction. But right now, as you can see, as I'm doing in the video, I'm adding some molecules or some particles around the two that want to bond here, okay? And you can imagine for a minute that these are gas particles. This might be two particles coming together in the air. You could also envision this as something like solvent particles. So I've got two particles coming together to make a chemical bond. All right, but we're doing it now in water as opposed to doing it in vacuum. Because again, if the two particles just want to make a bond in vacuum, they come together at super high speed, but then they can't bleed off that extra energy to maintain the bond. So watch what happens once we bring these particles in and make a bond with them, with these other particles just around there. Whoops, went too far. Sorry about that. And let me go to that part of the video. So here we go. So I'm just putting the particles in there. And I just put a few. I didn't think about it. Notice they're not moving. It's important that the solvent particles right now don't really have any speed on their own, although realistically at temperature, they would be moving too. This is just for the points of simulation. And I'm just going to rerun it. Got to move that one out of the way. You just can't have two on top of each other. And watch what happens now. The particles come together, but they run into the solvent as they come in. And as a consequence of running into the solvent, they make the solvent move faster. And as the solvent moves faster, they have bled away kinetic energy from the positive and negative particles. So now we have a stable bond. But as a consequence of having that stable bond, we're seeing that particles outside R2 that have made the bond have started to move around. So therefore, whenever we make a bond, I want you to see right away that this process must lead to bleeding velocity, bleeding kinetic energy off into the environment.
So Paul?
Yes, go ahead.
I'm just going to interrupt here and say,
sure.
It's terrific to talk about exothermic and all, but what observable would correspond to this?
That's an excellent question, Mr. Eckenpuro, what that would be in this particular case. So if particles are moving faster and have a higher kinetic energy, and we're going to see this in a second, what we would see is that, remember, temperature is the measure of average kinetic energy of particles. So since the average kinetic energy of the solvent particles, of the particles around the bond, has gone up, what we should see at that point in time is that the temperature is increased. So anytime we see a reaction like here, where just a bond was made, no bonds were broken, but just a bond was made, and there are many chemical reactions in which that can happen, and we'll see one here in a second, in which a bond was made, that process is going to be exothermic. So whenever we're making bonds, that process must release energy, because we got to bleed off this energy when it comes into play. And consequently, going back to the beginning of the video, notice that if I go back to the point where these two particles were coming together right here, you would have to do some work, you would have to do some pulling to pull these two particles apart. So the point that Mr. Eckenpuro is making from right here, and I'm going to write this right here on top of this, is that whenever we make bonds, that process is always exothermic. Making bonds is always exothermic, meaning we're always going to release energy into the environment when bonds are made. But when we break bonds, that's going to require energy.
And
so those process, go ahead.
And if you're doing this in the lab, what you're measuring is the temperature, which is you're measuring the surroundings. So
right. And we're going to see that in a
me.
lab in just a minute, that we're going to measure the temperature of the surroundings from right there too. And that's exactly right, because the problem is, going back to the video, the issue that comes into play is that we never really get to monitor the bonds themselves. What we get to monitor instead is what's going on in the environment. So if we were watching the environment right here, as this bond was being made, the only thing we really get to monitor in the lab are the particles around the bond. So therefore, if I know that I've got two particles, say here, making a bond, okay, the way I can figure that out is that I can watch the particles around that and see that their temperature goes up. And if their temperature goes up, that must mean that what was made was more stable than what we began with. So right now, I would have a thermometer in the environment watching these little particles move faster and faster and faster. But of course, we can't see that on a particulate level. And the only thing we can see is actually the increase in temperature. And interestingly, that little red bar on the right-hand side is meant to represent that in kind of an abstract way from right there. So whenever we see a chemical reaction in which the reaction itself is exothermic, or energy's been released in the environment, we know that the products of that reaction were more stable than the reactants of that reaction. Now, in this case, we just made a bond. What we're going to look at here is a situation where we both can make a bond and break a bond. So let's look at that in the next slide, okay? And so here's the first question. And I'm going to help you with this one because it's really hard to discuss this. It's not a multiple choice question. But one of the most interesting reactions we can look at is what's called the isomerization of hydrogen cyanide. So it turns out that the hydrogen cyanide molecule, and I'm going to go ahead and draw these Lewis structures. The hydrogen cyanide molecule, you can actually build as two isomers of H, N, and C. And the more stable one, the one that most people are used to talking about, is this molecule, HCN. And so let's quickly draw the Lewis structure of HCN as a review. So what do we need to know first in order to draw the Lewis structure? We need to know the number of valence electrons. And the number of valence electrons here, hydrogen would have 1, carbon would have 4, and nitrogen would have 5. So the total number of valence electrons would be 10. The next thing we need to do is we need to pick a central atom, okay, in this particular regard. And a couple remembers about central atoms, which they're actually trying to tell you in the picture. They're trying to say right here, hey, this carbon is central, and here this nitrogen is central, is that when we pick a central atom, one, hydrogen can never be a central atom because it only can form one bond, okay, on top of that, because you can only have 2 electrons to satisfy the duet rule for hydrogen. So remember, if you're trying to pick a central atom between atoms when you're building your own Lewis structure, you really want to pick the atom with the lowest electronegativity. And the reason for picking the lowest electronegativity is the fact that that atom can actually make more bonds and it doesn't mind sharing its electrons as much as, say, an atom like fluorine, which has an extremely high electronegativity. So therefore, what I'm going to do is I'm going to say carbon's my central atom. I'm going to put the other atoms around the carbon atom. And when I draw Lewis structures, I always make a first guess. So here would be my first guess for the Lewis structure. So I've made a single bond between the carbon and each of the other atoms, and then I'm satisfying the octet rule for everybody else and the duet rule for hydrogen. So we know that this structure would satisfy the octet rule. I have a single bond between the carbon and hydrogen, which gives hydrogen its 2 electrons. I put 2 unshared pairs on each carbon, and in this particular case, 3 unshared pairs on each nitrogen, again, to satisfy the octet rule. But when we look at this structure, we have a problem, because the structure I've drawn has 2, 4, 6, 8, 10, 12, 14 electrons, but I only have 10. So therefore, this structure is invalid because it violates the total number of valence electrons I have. What are we supposed to do in a case like that? That's when we want to build in multiple bonds. So what I'm going to do is I'm going to go ahead and build a different bond. I'm going to take 2 electrons away from the carbon, 2 electrons away from the nitrogen, and replace it in this particular case with a double bond. Well, if I do that, that's great, because the double bond lessens the requirements of the valence electrons on each of these on the outside, because the bonds are being shared, the electrons are being shared by both atoms. But if I count again, I've got 2, 4, 6, 8, 10, 12. I still have 2 too many electrons. So what am I going to do? I'm going to go build a third shared bond, the triple bond. And in order to do that, I'm going to have to remove electrons, that unshared pair from the carbon and that unshared pair from the nitrogen. And if we now have it, that triple bond allows us to have 10 valence electrons and satisfy the octet rule for everyone. So this would be the Lewis structure for HCN, okay, on top of that. Now, what I want to do right now is for HNC, the structure is exactly the same. We're not going to walk through the entire process for HNC, but what we can do instead is all that's going to happen in HNC is the triple bond is maintained, but the hydrogen actually now bonds to the nitrogen and the carbon has the unshared pair in HNC, okay? So this is hydrogen cyanide, all right, from right here too, and this is an isomer of hydrogen cyanide, which has the H and the C. So the question becomes, which of these arrangements are more stable, okay? Because we've made bonds in both cases. So therefore, since we've made bonds from atoms in both cases, what we expect is just like what we saw in the previous animation, that energy would have to be released when these bonds are being made. So how can I make an estimate of which one of these is more stable? Well, in order to make that estimate, I can come over here to this bond energy table, which is typically talked about when you talk about Lewis structures and electronic structure theory, electron configurations, et cetera. And if we look over here, we have bond energies for everybody. So the CH bond, I'm just going to write it down and re-highlight it, is 413 kilojoules. The NC bond, it's C triple bond N bond, which is the same in both from our perspective, is going to be 891 kilojoules. And the NH bond, looking up here, is going to be 391 kilojoules per mole. So if I want to calculate the amount of energy that would have been released in this top molecule, I'm making a C triple bond N, so I would release 891. And I'm also making a C triple bond H, so I'm releasing 413. So the amount of energy that would have to be released when I make these bonds would end up being negative 1304. That would be the amount of energy that would have to go into the environment. That would be kilojoules for every mole of HCN I make. Well, what about for this other isomer? Well, in this case, the H and the NC bond would still be the same, but here I'm making an NH bond. And notice an NH bond is not quite as stable as a CH bond. You release 413 kilojoules when you make a CH bond, yet you only release 391 when you make an NH bond. So in this particular case, I would release another 391. And so therefore 891 plus 391, and then we'll take the negative of that, is negative 1282. So although making both of these compounds is more stable than their individual atoms, making HCN is actually a little bit better than making HNC, okay? Because the bonds being made are actually, you have to release more energy, they are more stable. So HCN is a more stable molecule than HNC between these two. And we can use the bond energy table in order for us to determine that. Now, that also allows us to determine if you had a molecule of HNC and it was going to generate a molecule of HCN, what would be the energy change for the process? Well, in order to make this reaction happen, I would have to break this bond. And then, or excuse me, I broke the wrong bond. I would have to break this bond, excuse me for that, and then come over here and make that bond. So I'm going to break an NH, and I'm going to make a CH. Well, breaking an NH is going to require energy from me, and the amount of energy it's going to require from me is 391 to break the NH, but I'm going to release 413 to the environment to make the CH bond, and so therefore, net, I'm going to have a release of negative 22 kilojoules for every mole of bonds I break. So it turns out, according to our bond energy table, that HNC is more stable than HCN by about 22 kilojoules. Now, if we went into the lab, we would find out that these numbers aren't exactly the same. And the primary reason for that deals with the fact that these are average bond energies. This is taking into account every NH bond and every CH bond. And individual bonds have electronic environments that will make the energetics of them a little bit different. But the issue is that we get a good feel that HCN is a more stable molecule than HNC. So in this particular case, if this reaction were to occur, this movement of this hydrogen, we should see that the environment, the surroundings, would increase in temperature by an equivalent of 22 kilojoules, okay, from right there. But does that necessarily mean that this reaction would always occur, okay? And in order to answer that question, let's look at something else. Well, what's the stable state of water? Well, most of us would say, if we talked about the stable state of water, most of us would say, well, the stable state of water is a liquid, right? I'm looking right now, I have a drink right next to me. And clearly, the stable state of water, which makes up 99% of my drink, is a liquid. But the problem that comes into play is, what if I put water in a slightly different environment? For example, what if I heat up a pan significantly and then put water on that pan? Well, if that happens and I heat up water significantly and put it on the pan, that water immediately goes to its most stable state at that temperature, which is actually gaseous water. And of course, what we're seeing here is the water boiling away to make steam. So the most stable state of water, the state of water we would find in the environment, completely depends upon the temperature of the water. Well, what does that have to do with anything? Because we can see right now when he threw the water on the room temperature surface, it's liquid water. But when he had water in the pan itself, it was gaseous water, okay? So what is meant by that? Well, in order to go through that, we really need to talk about the most important, in my opinion, the most important thermodynamic variable, which is not energy change or enthalpy, change in energy from right there for a reaction. It's entropy, okay? And what we're gonna look at here is another video I put together, and I'm sure Mr. Eckenperr is gonna recognize from what program this video comes from, that deals with entropy from right there too. And what we see above is what your teachers have been working at for the definition of entropy from right here, okay? But what I wanna show you here is this is a copper bar, this is a bar of copper, and what's gonna happen is that the bar of copper is going to be heated. And so as I play the video from right here, I want you to watch over here, because what you can't see that's happening right here is someone has put, outside of this, someone has put a little teeny tiny flame on the left-hand side of the copper, okay? And they're really heating up the copper on the left-hand side. So we're gonna watch two videos of this, two simulations. Watch the first one, and if you can actually see what happens to the copper while it's heated. So watch the copper as it gets heated, there it is. And notice what you see happen is, as the copper gets heated, we start to see this jiggling of the copper atoms throughout the entire bar, you know? And so where the jiggling was really high initially on the left-hand side, that jiggling is basically propagated throughout the entire bar as the heating continues, all right, from right there. Now, we're gonna rewatch the same simulation, but now what I've done is I've colored the particles by their kinetic energy. So remember, of course, kinetic energy is the energy of motion. And since this whole copper bar is initially at a temperature like 25 degrees Celsius, all the particles in the bar are moving. And you'll notice that areas that have higher kinetic energy will be colored red, and areas that have lower kinetic energy are being colored blue. Remember, the person's heating the bar just on the left-hand side. So all the energy input into this system from right here is coming from this part right here. So the only place where people are heating the bar is right there. And watch what happens to the energy. So what we notice is as the bar heats, the energy expands. And what we're seeing happen is that the copper atoms are colliding with one another randomly. We're basically transmitting the original energy input, which is on the left-hand side of the bar, across the whole bar from right there to eventually we're the point where the whole bar is going to be jiggling faster, okay, where pretty much all that energy that was concentrated on the left-hand side has been dispersed throughout the entire bar itself. And that's what we mean by entropy. Entropy is measuring the ability to disperse energy throughout a system. So when we're dealing with things from right here too, the problem is that even though if I start energy input into the bar on this side, there is no way to keep that jiggling localized, because once these atoms start moving faster, they hit their next door neighbor, which hits their next door neighbor, which hits their next door neighbor, and so on and so on and so on and so on and so forth. And as a consequence of that, what we see is that energy always has a tendency to disperse. Always. It's almost impossible to keep energy concentrated in one location unless that location is completely isolated from everything else. Notice the person who heated the bar didn't do anything. The only thing they did is heated the left-hand side of the bar, and over a long enough period of time, if you had your hand on the right-hand side of the bar, you'd be in pain as that energy is being transferred to you. So what we want to define is that we're going to define entropy is the dispersion of energy. And the issue is that the reason why this is happening is a complete consequence of probability. That once these things collide, there's no way to prevent those high moving molecules on the left-hand side as they collide to not transfer their energy to the molecules on the right. So there is two molecules collide, one of them is going to slow down, the other one's going to speed up. And as that wave moves across from right there, we are basically distributing that energy throughout the entire environment. There's just no way that the collisions could occur on the left-hand side that would keep all the energy just on the left-hand side of the bar and nothing on the right-hand side of the bar from right there too. So when we're thinking about entropy, we want to think about it as a dispersion of energy, okay? And we want to look at that, hey, if you think about dispersion of energy throughout the universe, dispersion of energy is an extremely probable event. The universe is going to try and do whatever it can to disperse energy as much as possible, okay? So what I want to look at here is let's look at some examples of the dispersion of energy, okay? So the first one I want to play with is, for example, let's think about O2 at 300 degrees Celsius or water at 300 degrees Celsius. And which one of these two would have a higher entropy, okay, from right there? Well, let's first talk about what we mean by the problem of 300 degrees Celsius. Because in the case of 300 degrees Celsius, what we're saying is that we're giving a certain amount of energy to both the water and to the oxygen. So when I say 300 degrees Celsius, it's the same thing basically as saying this oxygen has so much kinetic energy, total energy. This water has so much total energy, and those total energies are effectively the same. So the problem is if I have an oxygen molecule and I want to give it X amount of energy, what can it do with that energy? Well, one of the things the oxygen molecule can do is move. And the water molecule could do exactly the same thing. It could move from left to right, as we just saw with that energy input in the copper wire, or as we saw the energy input of the solvent molecules. Another thing the oxygen molecule could do is it could rotate. Well, the water molecule can also rotate, but the water molecule has an advantage that oxygen doesn't have, because water has three atoms like a top water molecules can rotate in multiple different orientations, where really an oxygen molecule can only kind of rotate end over end effectively. So it turns out that a water molecule can rotate more ways than an oxygen molecule can. So I could take some of that energy of that 300 degrees and make the water molecule do a whole bunch of different rotations that the oxygen cannot. Finally, the other thing I could do too is I could make the bond between the two oxygens, which acts like a spring. I could make that bond get wider or get more narrow and have the oxygen vibrate back and forth. Well, in the case of the water molecule, though, I can make it vibrate in multiple locations because this OH bond can vibrate outward and inward, and this OH bond can vibrate outward or inward. So the problem that comes into play is that I've got a lot more things I can do with my energy in the water molecule than I can do in the oxygen molecule at the same temperature. There are more places to put that energy. Yes, sir, Lou.
I'm going to slow that down just a second because I'd
Sure.
love to make some connections with the previous units. And as we
Sure.
talk about molecular vibrations and molecular rotations, I believe, and you're the expert on this, that part of the curriculum framework talks about the electromagnetic spectrum and where we might find the energies of photons that correspond to these excitations.
Excellent question.
Will you digress just a little bit?
Sure, I'll be happy to digress a little bit on that from right there. So the
I
problem that comes into play, the problem that comes into play for us, and if we had more time, I'd actually put up in Spartan, but the problem that comes up to play for us is that, you know, we really can't see a bond vibrate or a bond rotate. So the issue that comes into play is that I can heat these molecules up. And when we heat those up, it's almost like hitting a piano and giving the molecules all sorts of energy and say, go do with it as you want to. Some of it's going to go into moving, some of it's going into vibrating, some of it's going to go into rotating. Well, another way to be more precise with actually adding energy a specific way is I actually could be like a surgeon and actually just make this bond vibrate on its own without really worrying about the rest of the molecule right away. And the way I could do that is I could shine light of a specific frequency onto that molecule. And the different motions, the different internal motions, vibration, rotation, and promoting electrons from one energy level to another, those ways of adding energy to the molecule, I could actually surgically do by adding light of the right color. And so as Mr. Akampuro was saying from right here, if I add light here that's in the infrared part of the spectrum, right, and remember the infrared part of the spectrum is going to be wavelengths that are just above the visible wavelength of the spectrum. So remember the visible spectrum goes from 400 to 700 nanometers, okay, where 400 is blue and 700 is about red. If you have wavelengths just above 700, which would be frequencies just below the frequencies of red, that would be infrared radiation. That would be heat, basically, as we would feel it. It would be like feeling the heat coming off of a lamp that you would see from right there. That would promote the vibration of the molecule. So if I just wanted to add energy into the vibration parts of the molecule, I would hit it with infrared photons. If I wanted to promote the rotation of the molecule, and unfortunately, this is something we don't really get to do in AP, we could hit it with microwaves. And in fact, when you're microwaving your food, one of the reasons why the food gets hot is that the microwave radiation is actually causing the water molecules in your food to rotate faster. And it's a great play because what happens is, although the energy starts in the rotation of the molecules, because as the molecules rotate, they hit their friends, that energy then disperses throughout the entire food as heat. So therefore, if I just want to promote rotation, I can promote it by microwave radiation. So that's what your microwave oven is effectively doing. Finally, if I want to just promote moving electrons, say I want to pull an electron out of this bond completely, the way I could do that is I could use UV radiation or higher. So if you start with UV radiation, that would start actually pulling electrons out of bonds or moving in between energy levels. And we could actually promote that to a little bit higher. X-rays could do the same thing, which is why we do not want to be exposed to UV radiation consistently, because those UV photons from the sun, for example, which could cause things like skin cancer, are causing that because they're disrupting bonds in the human system. So I can surgically add energy as I would want to by using light of different frequencies. But if I just want to flood the entire system and not worry about if energy goes to X, Y, or Z, then I would just hit it with just put it in a temperature bath. And that's going to be, as I said, like playing a piano, hitting all the tunes at once on the piano and flooding every particular channel of energy as I want to at that particular temperature. But going back to our entropy component from right there, what water has going for it is water has more ways it can store that energy than oxygen does, because water can vibrate in both the OH bonds, it can rotate in multiple dimensions, and it can move around. Oxygen can only rotate in one dimension, one type of rotation, move around and vibrate that one double bond. Because of that, I have more places to disperse energy in water. And because I have more places to disperse energy in water at the same temperature, the entropy of the water would be higher, okay? In contrast with part B, we're dealing both with oxygen in those parts in part B, but from right there, if I'm at a higher temperature, I've got more energy to play with. Well, if I have more energy to play with, I have more places where I can disperse it. So therefore, what we're always going to see is that think of energy effectively as the currency of chemical reactions. So if I want to disperse more energy, if I have more energy to start with, there are more places I'm going to be able to put it than if I have less energy to start with. So O2 at 0 is going to have a higher entropy than O2 at minus 50. The other thing we'll see too is that entropy is able to be dispersed if you can move energy throughout a container. So for example, if we were to look at a gaseous state, like I2 gas, which may on a particulate level look like that, versus I2 in a solid state, which would look more like this, the ability to send that energy throughout the container for each of the individual particles to explore the space and disperse that energy and matter throughout the container also increases entropy. So what we always see is that you're going to have a better ability to disperse energy in gases than you will liquids, and liquids than you will in solids. So I2 gas at room temperature, because it can move throughout the container, can disperse both matter and energy more than I2 solid throughout the container. So I2 gas will have a higher entropy. And then finally in D, D is kind of an interesting question, because if you have 1 mole of O2 at 2 different pressures, well, the only way you could have 1 mole at O2 at 2 different pressures at the same temperature is if the container volume of one of the moles of O2 was smaller than the other. So if I'm at 1 bar pressure for 1 mole and at 298 Kelvin, the only way I could be at 1 bar pressure, which is almost the same as 1 atmosphere, that's the SI unit of pressure, at 750 torr. The only way I could be at that is if the molecules are running into the walls more often. And the only way the molecules could run into the walls more often is if the box itself is smaller. So since the same amount of oxygen is exploring a larger space, this sample of oxygen would be at a higher entropy than that sample of oxygen. So what you want to look at when you're thinking about entropy is you want to ask yourself, how much energy do I have to disperse? Because if I always have more energy, there are more ways I can move it throughout the molecule. Or if I have the same amount of energy and I have 2 different molecules, the more places I can put it, okay, the more entropy that's going to come into play from right there too. And this is a very common question that we see both on free response and we'll see on multiple choice. There'll be a comparison between 2 substances from right there as well. All right. So with that in mind, one of the ways we actually measure that, and this is something we don't worry as much about in AP, is that we can actually put a number to the ways to disperse energy. So for right here, what I want you to look at right away is that we can put a number right here to the ways we disperse energy. So hydrogen gas, for example, at room temperature has an entropy of 130.7. Now, we're not going to worry about, although it's very interesting, how we actually get this number. But what I want you to think about is that at a given temperature, what this number is actually telling you is a numerical idea of the number of ways to disperse energy. And the only thing we want to play with here is that the larger that value of S naught is, there are more ways to disperse energy for a given larger value of S naught. And for those of you who take classes after AP Chem or after Gen Chem in college, you'll actually learn how to calculate this number. And it's a fascinating statement because you actually count the number of ways you can disperse energy. And this number here is directly proportional to that number of ways in an idea called statistical mechanics. But that's a little bit beyond the scope of our course from right here. But what I want to show you here is I want to go back to water itself. Notice I have liquid water here and I have gaseous water here. And so as a consequence of both having liquid and gas, I can actually tell you for this process, H2O liquid goes to H2O gas at any temperature. I can actually tell you for this process if the entropy change, if this is going to result in a greater dispersion of energy. Well, we would expect it would, because H2O liquid, although they're the same molecules, the H2O gas will disperse throughout the container and the H2O liquid would not. And if we look at the entropy values, we can see that the entropy value of H2O gas, and I'm just going to round it, it's 188.84. Let's just make it easy and call it 189. And this one's 69.95. Let's just call that 70. So therefore, if I look at it, we see that the delta S, the change in entropy, is 119. And the units of that kind of make sense. The units of that are energy, joules per Kelvin mole. And the way you can think about that is, this is how much energy I can disperse in 1 mole of water per degree Kelvin or per Kelvin. So for every Kelvin of temperature, I can disperse an additional 119 joules of energy throughout 1 mole of the molecule. I can disperse 119 more in the gas than I can in the liquid, all right, from right there. So what this is really telling us is that H2O gas, all right, has a higher entropy than H2O liquid, and that's what the difference is, all right, from right there, which is something we didn't worry about when we did our example from before. We're going to need that number in a minute, okay, as we move forward. Now, I want to remind you something as well, and if you've had a previous thermo lesson, you could actually talk about this aspect, because what we're going to see in the next slide, we're not going to have quite time to do, but it would be a great problem for you to do it on your own. Notice also that S here is not a delta. This is actually telling you the number of ways to disperse energy. In contrast, and we'll deal with this one later, but dealing here, notice this is not a heat of formation, it's a delta heat of formation. And remember, by definition, what this is telling you is the energy change in making a substance from its elements in their standard state. So the delta here actually is important because it's measuring this chemical reaction. So for water, liquid, it would be the reaction of H2 gas plus 1/2 O2 gas goes to H2O. It is the energy change for making 1 mole of product from their elements, and everything is what's known in its standard state. That would be the normal state you would find the substance, the elements, at this temperature. Well, the normal state of hydrogen would be a gas, the normal state of oxygen would be a gas, okay, at that given temperature. So it turns out right here that the energy change for this reaction for making H2O liquid is negative 285.83, meaning that liquid water is 285.83 kilojoules more stable than 1 mole of hydrogen and 1/2 mole of oxygen. Notice that gaseous water is not as stable. It's only negative 241.83. The only difference here would be making that a gas. Whoops, went too far. Well, why would that be? Well, the reason why that would be is because think about going from H2O liquid to H2O gas. I have to overcome intermolecular forces. Because H2O liquid, the liquid particles are moving around. They haven't quite overcome the intermolecular forces. And in the ideal gas sense, in H2O gas, everything is blown apart into individual gaseous water molecules. We've completely separated one water molecule from another water molecule. Well, in order to do that, I have to overcome, again, those attractive forces. And overcoming those forces is an endothermic process. So the difference between these two values, H2O gas here being negative 241, I'm going to write that right here. And again, I'm going to keep it just the nearest joule. And this one being negative 289, the difference here between those two, and in fact, if you do it, it's kind of cool because you see the 8 3s are the same from right there too. So the negative 285.83 minus 241.83, this difference turns out to be, whoops, I did it the wrong way, negative 285.83 plus 241.83, how's that? That difference turns out to be exactly 44 kilojoules per mole of reaction. So what that means is that although gaseous water disperses energy better than liquid water does, there's an energetic cost, because in order to overcome the intermolecular forces, I have to put in 44 kilojoules from the environment to make liquid water into gaseous water, okay, from right there too. But again, I want to highlight that this is a difference, which is why for elements, this number is 0. Because for elements, that would be making H2 from H2. How would I make 1 mole of hydrogen from its elements in their standard states? Well, I'm not doing anything to make H2 from H2, which makes these numbers 0. A very common mistake we see students make is they forget this is a difference, and this is actually a way to count. You will never see a table like this with a delta S. The S is counting the number of ways to disperse energy, and the table here is counting the difference in energy between the elements and the products we're making from right there too, okay? And that's something very important to think about as you're doing the mathematics here, because it's really easy to make careless mistakes. One other point I want to bring up too that we're going to see from right here in the calculation we're about to do is that notice in delta H, those units are usually in kilojoules, and in S, they're usually in joules. And so therefore we have to worry about a conversion factor in order to make that happen from right there too. So going back to this process, notice that the universe seems like it would love to make gaseous water, because in gaseous water, we can disperse energy better, but there's a cost. And the combination of those two is going to show us what's going on here and determine the thermodynamic favorability reaction, as we're going to see in the last 15 minutes we have together. Now, one exercise I have for you that we're not going to have time to do, but this would be a really good exercise for you to do. As I said, Mr. Akinpura will have the PowerPoint that you can do it, is that I've actually done an experiment for you to measure the heat of vaporization of water. And just to give you a quick heads up of how this experiment works, is on the left-hand side, I have 5 mils of water that I'm about to boil. On the right-hand side, I have 100 grams of water or 100 mils of water that are going to heat up. And what we're going to end up doing is, if you run through the simulation, I'm just going to do it super fast. Okay, I heat up the solution, and this temperature gauge on the right is measuring the temperature of both water samples. It's really measuring the temperature. I should take that back. It's not measuring the temperature of the water sample on the left. It's only measuring the temperature of the water sample on the right. And so therefore, as this heats up, there comes a point in time, that's 5 mils, and that's 100 mils, where the water starts to boil. And I'll tell you where that is. Right there, that water starts to boil. Well, remember, when water boils, its temperature stays constant, because what's happening there is that all the energy is going into overcoming intermolecular forces. But if we make the assumption that all the same amount of energy is adding the boiling water is adding into the liquid water, we can actually count the amount of energy it takes to boil the water by watching this liquid water and watching this temperature. So right now, I have 100 grams of water at 41.9 degrees Celsius. And as the process occurs, you'll see the water on the left begin to boil away, and the water on the right increases in temperature. Well, if the hot plate is giving the same amount of energy to both samples of water, and that's the assumption we're making, that the hot plate is doing that, then therefore I can use this as a way to determine what the heat of vaporization of water really is. And I'll show you there's a point where the water goes away. There it is, it's gone. And the temperature of the water has gone up to 69.3. If we had enough time, I would have you actually calculate the enthalpy of vaporization this way experimentally. But you can use this as an example on your own, since you're going to have the PowerPoint. And of course, we should get a number really close to 44 kilojoules per mole. It won't be ideal because of the approximations we're making, but that's one way experimentally we could actually measure this number of 44 kilojoules per mole, okay, from right there. Now, how does this water problem come into play? So what I want to do is, very quickly, is let's calculate what's going on here. And I'm going to go back and use the numbers. So let's write down the reaction. So we have H2O liquid goes to H2O gas. We know that the delta H, the energy change for this process, is 44 kilojoules. And we know the enthalpy change for this process, delta S naught, is 119. And remember, this is in joules per Kelvin mole, and this is in kilojoules per mole. Now, here's the problem with all this. The most important law in all of thermodynamics, what drives everything in the purposes of this whole presentation, is that energy naturally has a tendency to disperse. And we've seen that with the copper bar. We've seen that kind of across the board with individual atoms or molecules. Energy is going to have a natural tendency to disperse throughout the universe. But the issue is that it doesn't disperse in the molecules. It doesn't disperse in the area around the molecules. What the universe wants to have happen is that the total amount of dispersion goes up, because that's much more probabilistically likely for the total energy dispersion to go up than for it to stay concentrated in one location. So the second law of thermodynamics says, hey, for any process, the total entropy change of the universe must be greater than 0. So if the process allows energy to become more dispersed in the universe, that process is going to happen just because it's more likely. But since it's the universe, we have to consider both the system and the surroundings. Well, the problem with water boiling is this. Water boiling is great for increasing entropy because its change in entropy is 119 joules per Kelvin mole. But the problem is the entropy of the surroundings is going to go down. And the reason why it's going to go down is that I need to take energy from the environment to make the water change from liquid to gas. It's an endothermic process. Well, if I pull energy from the environment, I'm reducing the number of ways to disperse the energy. Because if there's less energy around, there's going to be less places to put it, or different ways to put it. So as a consequence of that, the entropy change of the environment is going to drop. Well, what the universe doesn't care about the system, the universe doesn't care about the environment, the universe cares about the universe. So if the process overall is negative, the universe is going to say no. If the process is overall positive, the universe then at that point would say, I'll let that process happen and make a significant amount of product. So the question becomes, how do we calculate this? And this is something you don't need to really worry about for the AP exam, but I want to show you where the numbers come from. And then as we lead off to the transformation of delta G0, it turns out the way you calculate the entropy change of the surroundings is you just figure out how much energy the surroundings is changing, which I'm going to call Q, that's the amount of heat energy, divided by the temperature at which it occurs. So for example, this process here, this delta H, we're going to assume is constant for all temperatures. At 25 degrees Celsius, it takes 44. At 30, it takes 44. At 40, it takes 44, and so on. So the entropy change of the surroundings I can just calculate is always going to be negative 44,000, because again, I have to be in joules, so my units are consistent, divided by the temperature at which the process occurs. So let's try something at 298, okay? We know at 298, water is a liquid, it's not a gas. So at 298, let's calculate the entropy change of the universe. Well, that would be 119 minus 44,000 over 298. Well, what is that? Well, 119 minus 44,000 divided by 298 is negative 28.7. Now, I really don't care what the value is, okay? What I care about is that it's negative. And because it's negative, what the universe is going to say, if a significant amount of water goes to products, then the entropy change of the universe is going to drop, and that's less likely. It's a less dispersion of energy. Therefore, it's not going to happen because it's not as probabilistically likely as keeping the energy more dispersed in the liquid state. So therefore, at 25, water stays as a liquid. Now, we can do this in the same calculation. We could do it again and again and again at multiple temperatures. So here's what I want to show you. Here's a list of doing that same process, just calculating the entropy change of the system. And notice it's always 119. And the entropy change of the surroundings, which I'm getting is negative delta H over T for a whole bunch of temperatures. And then here's the sum. Well, notice interestingly what happens. At 77, it's still negative. At 85, it's still negative. But we get to 105, and that process becomes positive. We'll recognize what we know at 105. At 105, what state are we going to find liquid water at? We're going to find it as a gas. And the reason we're going to find it as a gas is that at 105, the entropy change of the universe is positive if water exists as a gas as opposed to existing as a liquid. And same thing's true at 103 and 101. Now, what's interesting is where that number gets to be 0. And for us, that number gets to be 0 right around 97. Well, using the data we have. Where it really should be getting 0 is at 100 degrees Celsius. And the reason why we're not seeing it 0 at 100 here is because these values, this delta S, remember this was calculated at 298, This is being calculated from a delta H at 298. And these numbers actually change a little bit with temperature. We don't worry about it, but they do. We usually make the assumption that they stay constant. Well, because they're changing a little bit with temperature, I have a little bit of error here. And as a consequence of having a little bit of error here, I'm getting a positive shift at 97, where I should really get it at 100. And where it would sit at zero, basically the universe is saying, hey, liquid water, gaseous water, I don't care. And as a consequence of that, since it doesn't care at zero from right there, that's when we're in equilibrium between the two states. So ultimately, go ahead, Lou.
This might be a good time to remind you we're about 127 now. So
thank you, sir. Well, I'll be done. I'll give me 5 minutes and we'll be over right there too. So therefore, as we go through that the universe only cares about the system as a whole. Now, let me bring that over for the next piece here. The problem is that we never have students calculate delta S of the universe. So this is what we have them do instead. I just want to show you something. So if delta S of the universe is delta S of the system plus delta S of the surroundings, I'm just going to do a little bit of work, okay? We want this number to be greater than zero. So in this particular case, how did I calculate delta S of the surroundings? Well, I'm going to take delta S of the system, which I'm just going to call delta S naught, and say, hey, I calculated that by taking delta H naught over T. That's how we calculated delta S of the surroundings, and that's greater than zero, okay? Let's do a little bit of math. T has to be in Kelvin. So since T is in Kelvin, it's always positive. And if I just do a little bit of rearrangement, I get this. So delta S of the universe being greater than zero is equivalent to this term being less than zero. And we call this term the Gibbs free energy. And one of the main reasons we have you calculate that is that notice now, you don't have to worry about this annoying delta S of the surroundings or this annoying change in sign, because if the reaction is endothermic for one thing, it's exothermic for something else. So what that means is that if delta S of the universe is greater than zero, the reaction will be thermodynamically favorable. That's equivalent to delta G naught of the reaction being less than zero. So therefore, what we're going to have you do in AP is we're always going to have you calculate delta G naught of the reaction, okay, from right there. So look at that in the context of our water, okay? This graph shows what happens to the entropy change of the universe, all right, as the reaction proceeds. So here is 370 degrees, okay, from right here. Notice over here, delta S of the universe, okay, is negative. Here, delta S of the universe is positive. The green line shows you what happens to delta G naught. Over here, delta G naught of the universe, or delta G naught of the reaction, is positive. Over here, delta G naught of the reaction is negative. So anywhere the entropy change of the universe is positive, the free energy is negative. So by combining all this information into one equation, if you can simply calculate the delta G naught of the reaction, you can right away determine if the reaction is thermodynamically favorable or not. If delta G naught is positive, it won't be favorable. If it's negative, it will be favorable, all right? And then to wrap up from what we have from right here, let's go back very quickly to our example. And then I'm going to give you a written value of all these questions from right here in the example, if you want to work it out on your own after we're done, and then you can compare it to the writings I'm going to give Mr. Akinpura that he can put on the Google Drive. So let's go back to our example from before, okay, with the 3 students and the reaction. Well, Linda is incorrect because we just saw reaction, or what we could see is that even if a delta S naught of a reaction is negative, it could still happen if the entropy change of the surroundings were positive. If it were more positive and delta S the reaction were negative, you could have a reaction that's thermodynamically favorable. Paul can be incorrect because delta H doesn't tell you how you're going to disperse energy. The only thing it tells you is that you're releasing energy, not where you're putting it. Kim is always typically going to be the one that's correct because thermodynamic favorability for most reactions depends upon temperature. And if we go back to the reaction we were looking at, I want to talk about it conceptually, and then I'll let you work it out. Look at the reaction right here. We're told that delta S naught is negative. And the first question here is, how could we say that with particulate level reasoning? Well, notice here in the original situation, we have all these particles moving around as a gas. And as a gas, then they're dispersed throughout the entire container. And then they get condensed down to a liquid where they can't disperse or send their energy throughout the container as much. And as a consequence of that, all right, on a particulate level, the entropy is negative. Well, even though the entropy is negative here, I'm going to tell you right here, when you do the mathematics, you're going to find that delta H naught is also negative. Whoops, went one step too far. So delta H naught is also negative, and I'll let you calculate. Well, if delta H naught is negative, look at the equation for delta G. Since delta G naught is delta H naught minus T delta S naught, we have a scenario where there are four things we can look at. If delta H naught is negative, that means we're giving the environment energy. If delta S naught is positive, that means the reaction is also increasing in entropy. So the entropy of the surroundings is going up and the entropy of the reaction is going up. So therefore, this reaction would always be favorable. In contrast, we could have a process where delta H is positive, meaning the entropy of the surroundings is dropping, but also delta S is negative. The entropy of the reaction is dropping. This is a big no-no for the universe, because the universe is never going to let that happen. The two scenarios you're going to investigate in this problem are the scenarios: what happens if the entropy of one of them goes up, but the entropy of the surroundings goes down? Well, if the entropy of the reaction goes up by more than the entropy of the surroundings goes down, then that reaction could still happen. We could also have the process where the entropy of the surroundings goes up, but the entropy of the reaction goes down. Well, now in this scenario, if it turns out that I can generate more entropy in the environment than the reaction has, that reaction can occur. And as you're going to see mathematically, one of these happens at higher temperatures and the other one happens at low. It'll depend upon what the temperature is. And as you work through this example, what I want you to be able to do is actually calculate delta G naught on your own, and then compare it to what I've done. And we'll show you on the handout that I'm going to give Mr. Akampura. And you're going to see at 25 degrees Celsius, overall delta G naught will be negative. And since it's negative, it's going to turn out that the entropy we're generating in the environment will offset the entropy loss of the system. So whenever you're looking at a chemical reaction from right here, that's what you want to think about as we go through review. And that's why delta G naught is the most important property you're going to have in any reaction system from right there too. So this problem will be worked out for you. I invite you to take it, to try the problem yourself and calculate delta G naught your way and see if you agree with my work. And this is what you want to think about for any chemical reaction in terms of its thermodynamic favorability. And with that, Mr. Akampura, I'm going to turn it back over to you.
And welcome back. I'm going to, without further pontification, turn the gavel over to Professor Gelder, who will talk a little bit about electrochemistry and some hints that will get you through the AP Chem exam.
Yes.
Take it away, Professor.
All right. I'm gonna sort of switch to share my screen to get my iPad up so you can see the PowerPoint, which some of you may have already. I've sent it out twice. And so hopefully if you had an older PowerPoint of the electrochemistry topics, that you've got a newer version, but I'll point out where I went astray on the older version.
You mean where you were testing the students to see if they'd catch your errors?
Right. Oh, I could turn it sideways so it's bigger. Lisa is making, that's much better. I agree. All right. So I agree with Mr. Price that everybody is sort of approaching panic mode. My students this semester are also likewise approaching panic mode because May 6th I think the AP exam is May 7th.
First administration.
Or May 25th or in June, yes. But my students have their final on May 6th, which will not be as broad, the questions anyway, as the AP exam, but my students will have to do electrochemistry also. In fact, if Lou is recording this, I may even grab that to let my students look at the same information.
And those would be Oklahoma State students on the college.
Yes, Oklahoma State students. I'm sorry. Right. I am teaching students this semester. I've got 20 students this semester, so it's a nice small class, about 1/10 my normal population. Anyway, here are the equations from the equation page that are relevant for thermodynamics and electrochemistry. And what Mr. Price was talking about with delta S and delta H and delta G, you can see near the top of the left portion of the equations, and the one, delta G equals delta H minus T delta S, which he was sharing right at the end. And then below those are the equations that are relevant for electrochemistry, for that we will be talking about. And the minus NFE0 is equal to delta G. And then the Nernst equation. And the Nernst equation is on the equations page, but it's interesting. I think that we should look at that equation a little bit differently than the equations above it, because I don't expect that we will see questions that require the actual calculation of a cell potential of an E cell under non-standard conditions, which is what this equation addresses, because it would require too many points to be attributed to just one equation. And so we will do a couple of examples where we will use the Nernst equations to help justify our prediction, our three-headed coin. And then one equation which is sort of on the equation page, but not on the equation page, if you can imagine that, we can get by equating these two equations, the NFE0 minus NFE0 equal to minus RT ln a K, that we can equate those and just solve for E0 and get a relationship between E0 and the equilibrium constant as RT over NF times ln a K. We can get this equation also from the Nernst equation, but that's sort of an equation that's not on the equation page, but it is there. An important constant, the Faraday constant, 96,485, or what I like to call it, 96,500 coulombs per mole of electrons. So those are equations that are on the equation page that are available to you throughout the exam. Equations that are relevant to electrochemistry, which are not on the equation page, is this E cell is equal to E cathode minus E anode. And then I have rewritten the I equals Q over T for the relationship between coulombs and amp seconds, or the flow of charge over time. So those are equations. So what I was going to sort of talk a little bit about, I'm going to focus on this part, but I wanted to just, students on the AP exam are frequently asked to justify whether a reaction is oxidation reduction reaction or not an oxidation reduction reaction. And it's something that we have to be able to look at pretty quickly. And one way to tell whether a reaction is an oxidation reduction reaction is to focus on elements. If we have an element in a chemical reaction, that reaction is going to be an oxidation reduction reaction. And we can also notice the fact that sulfur on the reactants in the first equation has no oxygens, and sulfur on the products has 2. In the second equation, sulfur has 2 oxygens on the reactants and 3 on the products. And here, carbon has no oxygen, but now it does have oxygen. So those are one of the ways that we can classify reactions as oxidation reactions, because an element gains oxygen. And we look at the fourth equation, we see mercury has oxygen as a reactant and not as a product. So that's sort of the historical definition of reduction. So the terms oxidation and reduction have historical significance in the gain or loss of oxygen, but we have expanded our definition to become related to the electrons, loss of electrons and gain of electrons. And so the loss or gain, those terms have now flipped, where we talk about loss of oxygen was reduction, and gain of oxygen was oxidation. Now we talk about loss and gain of electrons, which are just the opposite. And so we've got little mnemonics. We've got LEO and GER, or oil rig, which is important in Oklahoma, to help us sort of keep track of the more modern, the current definition of what oxidation and reduction are. And so here are a bunch of reactions, which you can look at later. These are all oxidation reduction reactions, and you can classify those by seeing. We can see here, oh, there's an element here, here's an element. So those have to be oxidation reduction reactions. Over here in the third equation is an element. And these reactions are not oxidation reduction reactions, but that we classify here, we can classify as a neutralization reaction. Second one is just a decomposition reaction. We see there are changes of number of oxygens around carbon, but we have to be careful because for carbon, carbonate and CO2, there is a loss of oxygen, but when we think about the change in oxidation numbers for carbon, we don't see any change, which is a characteristic. Change in oxidation number is a characteristic of an oxidation reduction reaction. So these four are examples that are not oxidation reduction reactions. So I'd like you to, I think Lou will put up a poll for us. And so I would like to know which of those processes represent reductions, is an example of a species being reduced.
They can select more than one here or just one?
Oh, you get to select more than one?
If there's more than one to be selected.
Okay.
Would you rather is there only one right answer? Should I?
There is only one right answer.
Oh, well, I'll change it. No one's, okay, well. I'll leave this up. So let's go.
All right, so we've got one answer in about 25 seconds. So
we
that's
don't have a lot of students here, so we may
gained
not
about 65 seconds and answering. Oh.
And I'll just pop in. This would make an excellent, as Dr. Gelder's saying, this would make an excellent multiple choice question on the exam itself. We would see something with this. The only difference would be on the AP exam itself, we'd only have 4 choices as opposed to 5. But besides that, it would be an excellent question.
Yeah. Okay,
It's been a minute. I'm going to end the polling here.
right.
And John, you should be a co-host. You can actually launch.
Oh,
the
so I
poll.
can share the results.
So I'm,
Okay,
but I am
so
here.
we will share the results. And so the correct choice is D. If we remember just those historical definitions, in the case of D, we can see there's three oxygens around nitrogen and it goes to one oxygen. And so that's a loss. So that's a reduction. We can see in E, that would follow the case of an oxidation from a historical standpoint reaction. It's the gain, sulfur's gaining in oxygen. And in the first three, they've pretty much follow the modern definition in terms of number of electrons, the loss of electrons. And you can see in each case, to balance those half reactions, we would have to add an electron. Loss of electrons is oxidation. So we've got 4 oxidations and 1 reduction. So for the student who picked D, as long as you didn't pick any other ones, you're good to go.
Before you move on from there,
Yeah.
John,
Yes.
it's not real obvious because where the electrons are going, because you've got a negative charge on the left and nothing on the right. So maybe you could talk about oxidation numbers briefly. Although it should be a reminder, students need to be able to, calculate oxidation numbers quickly.
Right. And let's actually, I think in this next choice, the next multiple choice, let's go down here. Here I have shared the rules. So I'm going to go ahead and, I don't know if, I think everybody can sort of move the poll. Here are some rules for oxidation numbers that I would certainly recommend that students sort of commit to memory, or if you practice enough, these rules will be committed to memory very easily. And we can apply these rules back on that multiple choice, in that when we see an element in its standard state, that oxidation number is 0. So for calcium in choice A, it starts out with a 0 oxidation number and it goes to a +2. So an increase in oxidation number is an indication that electrons have been lost. And so increase in oxidation number. In the case of B, mercury is a 0, and we can see that Hg subscript to 2+, that the mercury in both mercury atoms in this case have a +1 charge. So again, increase in oxidation number, loss of electrons is oxidation. And then it's very obvious for the ions in third case, Fe2 and Fe3. But now when we get down to nitrate ion and NO, it becomes a little more complicated, because we have to remember, and in the listed rules, we have that oxygen in its chemistry generally has an oxidation number of -2. And so when we look at the sum of the oxidation numbers for nitrogen oxidation number plus the oxygen oxidation number, we've got 3 oxygens. They have to equal the total charge on the ion. So we have 3 -2s, and it's going to equal a -1. And so the charge on the nitrogen, which has a greater variability of possible oxidation states. In fact, nitrogen is one of the most variable. We don't see as much variability in nonmetals as we do in metals, but nitrogen has very high variability. But in this case, it would be a +5 plus a -6 to get a -1. And then as NO, since oxygen is a -2, your nitrogen is a +2. So the decrease in oxidation number from a +5 to a +2 is indicative of reduction. And typically for questions on the AP exam where students are expected to justify their selection of a reaction, a chemical equation, as representative of an oxidation reduction reaction, students must represent that with a change in oxidation state. So they must find elements in the reactant, an element in the reactant, an element in the product, the same element, and show their oxidation number values. You don't have to show how you got it, you just need to assign an oxidation number, a correct oxidation number value. And then in the last case, we see that sulfur is going to be a +6 in sulfite ion. And it's going over to, I'm sorry, this is a +4. Yeah, +4. Go up and get rid of that. And it's a +4 and a +6. So again, a gain in oxidation number is indicative of oxidation. So maybe you remember the rules for oxidation numbers. So let's look at this multiple choice question. We've got a nice complicated reaction up here. Which element is being oxidized during the titration? And what is the element's change in oxidation number? So I'm going to go ahead and relaunch the poll.
I'm going to put up the poll that has only one correct answer.
Okay.
Or one
Thank
choice,
you.
so sorry.
That's okay.
So there you go. And obviously no one should be picking E. That might be all we're going to get here.
Think so? Okay. All right.
Oh, no, we have.
So, yes.
Okay, our last, we get a few more.
So we can see, okay, I can go ahead and share the results. So in this case, we can see, just looking at the equation here, MnO4 minus is going to Mn2 plus. So we loss of oxygen, that's going to be reduction. So we can dismiss the manganese because it's being reduced. So it is in fact the oxygen in peroxide. This is a special case where the oxidation number for oxygen in peroxides is -1. And over here, we can see, we do see that there's oxygen here that's a -2. The oxygen here is 0. So we sort of have to be on our toes to recognize that there's oxygen in the MnO4, and it's, we don't specifically assign oxygens from in one reactant to oxygens in a product, but the possibility that we've got peroxide producing oxygen, -1 to 0. That's our oxidation. The increase in oxidation number is representative of oxidation. And so it's a little bit tricky going from -1 to 0, but that is getting more positive. So how we use oxidation numbers. And this is actually, we can take a moment just to talk about this particular kind of question as representative of some multiple choice questions on an AP exam. That there's a lot of information here that really, while very true statements about this particular titration, are really probably not relevant to the question that is being asked. And so I wouldn't say that this happens on many of the multiple choice questions on the AP exam, but it does happen on occasion. And one has to sort of be aware when you're doing the multiple choice portion that possibly there may be information that, while correct and useful information, it may not be relevant to the question at hand. So if it were a set, right, Lisa has a very good point. If it were a set, this information that was not relevant for this question in the context of oxidation reduction could be relevant in another part of the reaction, maybe related to stoichiometry. So, so let's go ahead and look at our first question. Our first question is going to be pretty representative of many questions that appear on the AP exam, and that is about electrochemical cells. And I have been thinking lately, just as a brief aside, we'll come back to this problem in just a moment, about the relevance of electrochemical cells, because we know electrochemical cells more as batteries. And we're going to look at a battery, but it's a pretty old and not very useful battery. But in the context of the components of a battery, the ones that we're going to talk about in a Voltaic or galvanic cell have all the components that modern batteries have. And I would say that, and I always say this, and I think it's a true statement even today, that battery chemistry is sort of, it's the modern day alchemy. There's really very challenging chemistry that's going on in batteries. And as we're all aware, batteries are becoming more and more important. In fact, I just saw a brief news report of a plane that is now is powered by batteries. And so it's the distance it can fly with 3 passengers is only 100 miles, which is not particularly useful, but batteries in their evolution as energy, portable energy sources is at their infancy. And so if I were recommending to a student about maybe a potential future, there's a famous movie, a well-known movie where somebody was whispering into somebody's ear that polymers were the most important thing. Now it's batteries. I think batteries are really where it's really exciting chemistry and engineering if you want to mix your skill set. But anyway, so here's an electrochemical cell. We've got a reaction that I think quite clearly is an oxidation reduction reaction. And the first 2 questions we're going to omit. I left them on there because we're getting close to having to do the AP exam, and as you're well aware of, some of the free response questions jump around in their topics, and so I'm going to leave those on there. You can address those on your own, but we're going to focus on C, to identify the species that's oxidized or reduced. And so I'm going to relaunch the poll, and you've got 4 choices there for who's being oxidized. All right. So I'm going to go ahead and end the poll. We've got four responses, and I'm going to share the results. And so choice A is the correct choice. Aluminum is the species that's being oxidized. The other choice, zinc ion. Zinc ion has a +2 charge. It's going to 0. And so believe me, this is a very common error that students are going to make. It's just a matter of practice, because oxidation reduction can be very confusing. You know, a decrease in oxidation number, or the loss or gain of our electrons. And sometimes with all of these different things going on in our brain, they can get jumbled. So just watch out for that, practice a little bit, but it is in fact aluminum that's being oxidized in this particular case. And so here's our next sort of oxidation reduction reaction. And I'm going to go ahead and relaunch this poll, and I'm just going to babble for a moment. But here I'm sort of showing you an empty galvanic cell, and share with you that the left portion of the cell is the anode compartment. And what I'd like you to do is to tell me what the species would be that's going to be the anode composition of the anode. And while we have not specifically made the connection, but one of the half reactions, whether it's the oxidation or the reduction half reaction, one of those half reactions must occur at the anode. So, yeah, it has. So I'm going to go ahead and, okay, we've got, does anybody else want to get in on this poll? All right, I'm going to go ahead and end the poll and share the results. So in our oxidation reduction reaction, which is written at the top, we recognize that aluminum was being oxidized. And so we need to remember that oxidation always occurs at the anode. So batteries, electrochemical cells, have 2 electrodes that electrons will flow between the anode and the cathode. And the important characteristics of anodes and cathodes, they must be able to conduct electrons. And so we make sure they're metals. And in this particular case, the anode is aluminum. And here in a moment, I'm going to give you another multiple choice question where we talk about the cathode. But let's go ahead, and I'm going to relaunch this poll and ask about the nature of the ions that are in the anode compartment. Because the anode compartment has to have a solution that contains particular ions as well as the electrode. So I've gotten one response very quickly. And again, this is 5 choices. The AP exam will only have 4 choices. So if anyone else wants to get in on this poll, I'm going to go ahead and end it and share the results. And the correct choice is B. We do need both aluminum ions and nitrate ions in the solution that the anode material is immersed in. So, okay, so this talks about the anode compartment. So let's do the cathode. If the right portion of this cell is the cathode compartment, what material, what's the composition of the electrode in the cathode compartment? Oh. Ah, okay. Yeah. All right. So I'm going to go ahead and end this poll, and I'll share the results. So in this case, again, we want a composition of the cathode electrode to be able to conduct electrons. And so this needs to be zinc. The anode we had as aluminum. So we had aluminum ions and nitrate ions in the anode compartment. And so the cathode material needs to be zinc. We don't want to pick zinc ions for the cathode because, again, that's not a solid. We need a metallic substance. And there are some occasions where the oxidation reduction reaction that's occurring in the electrochemical cell doesn't have a solid involved in it. For example, the reaction with permanganate, MnO4 minus, going to plus 8H plus 5 electrons going to Mn2 plus 4H2O. There isn't a metal in that half reaction, yet we still need an electrode with metallic composition. And so sometimes platinum is a nice inert metal that's not going to cause any side reactions from occurring. And so, but in this case, zinc is going to be the preferred choice for the composition of the cathode. And then maybe real quickly, I'm going to stop sharing and relaunch the poll to select the ions that would be in the cathode compartment. So I'm going to go ahead and end the poll and share the results. And yes, I agree, we would need zinc ions and nitrate ions in the cathode compartment. So next, we have the salt bridge. And the salt bridge, in this particular case, contains potassium nitrate, a saturated solution of potassium nitrate. And so while electrons flow from anode to cathode, we need to balance charge, as we'll talk about in just a moment. And so ions have to flow in the salt bridge to balance the charge. And so what I'd like to know is what ions are going to flow. And notice from left to right, from left to right would be this direction. So I want to know, do electrons flow from left to right? Do cations flow left to right? Do anions flow left to right? Or do cations and anions flow left to right? Oh, I got to put the poll up. I didn't relaunch the poll.
I can get it for you.
I got it.
You got it. You're doing so well, John. I was
Yes, you were
asleep
that's
at the
okay.
switch.
That's okay. Because this is a tougher question than the others, because we have to think about what's happening
And
at
why?
each of those electrodes. So I'm going to go ahead and end the poll and share the results, because we've got B, and D as the answers that are selected. And I'm going to say that B is the correct choice. We saw that at the anode, we have aluminum going to Al 3+ plus 3 electrons. And at the cathode, we have 2 electrons plus zinc ion going to zinc metal. And as the electrochemical cell discharges, we're producing cations in this solution. We're increasing cations, but over in the cathode compartment, zinc ions are plating out onto the electrode. So cations are being removed from the cathode compartment, but cations are being added to the anode compartment. So when we think of the salt bridge, cations always flow towards the cathode and anions flow towards the anode. And so it's actually pretty easy to remember, because of the nature of the cations and cathode, to remember which direction ions are flowing in the salt bridge. However, many students will claim that electrons flow in the salt bridge, and we have to remember that electrons only move in wires, not in solution. And so charge is balanced in solution by the flow of ions, while charge is balanced on wires through the movement of electrons. So there's our electrochemical cell. And now what I'd like to know is, if the standard cell potential for this reaction is plus 0.9 volts, and the standard reduction potential for zinc ions is minus 0.76 volts, can you determine the standard reduction potential for aluminum ion, 3 electrons plus aluminum ion going to aluminum. And if anyone is unsure about the mathematical equation that we might use to answer this question, all right, so we're getting some responses, sweet. So I'm going to go ahead and end this poll and share the results and remind the relationship that I had shared that was not included on the equation page, how we calculate cell potentials or calculate half reaction potentials, reduction potentials. This equation, E0 cell is equal to E0 cathode minus E0 anode. The E0s for the cathode and the E0 for the anode are reduction potentials, or standard reduction potentials. And you know that we only provide standard reduction potentials. We don't ever ask for standard oxidation potentials. We don't have tables of standard oxidation potentials because we're only interested in standard reduction potentials. And so in this particular case, we know the overall cell potential is 0.9 volts. We know that the potential for zinc 2 plus is the standard reduction potential for zinc 2 plus is minus 0.76, but we know that the zinc electrode is at the cathode, and so this is going to be a minus 0.76 volts, and that's going to be for the cathode. So now to solve for the standard reduction potential at the anode, we just need to do this algebra. So I'm going to move the minus 0.76, add 0.76 to both sides. And when I do that, I get a plus 1.66 volts is equal to a minus E0 anode. And so the E0 standard reduction potential at the anode is a minus 1.66 volts. And so C is going to be our best choice for this. Pardon? So this is a tough question because we have to be careful. If we approach this problem like in a lot of other cases, we look at this reaction as involving the oxidation of aluminum plus 3 electrons and the reduction of zinc 2 electrons plus zinc 2 plus going to zinc, that this is minus 0.76 volts. This is now a plus 0.9 volts. The sum of these two, the Al plus zinc 2 plus going to Al3 plus zinc ion, that it is a plus 1.66 volts, but this plus 1.66 volts is the oxidation cell potential, half cell potential. We were asking for the standard reduction potential, which is the opposite sign. We have to flip this equation, this half reaction, we have to flip the sign from positive to negative. And this is a very This is a very common question, either in a multiple choice environment or in a free response environment, where students will get confused about the sign. And this is the reason why I like us to remember this mathematical equation, because that mathematical equation always calculates the standard reduction potential. We always use standard reduction potentials for the E zeros at the cathode or the anode. So now, to bring home the thermodynamic aspect of this, of the electrochemical cell, is to, okay, so I'm trying to find my mouse. Where did my mouse go? Okay, Lou, I may need you to run this poll.
I can do that.
My mouse has gone off. Oh, there it is.
It found the cheese. Has your mouse found its cheese?
Yeah. So my mouse is back. It was hiding from me, camouflaged. So all I'd like to know is, is the cell reaction, the delta G for this reaction, going to be positive, negative, or zero?
And John, we're just coming up to 2:30 now, so this might be our last last question for our students.
I can do that.
That's okay. And some comments, but it also kind of talks about what we mean by the delta G naught, because in one sense it's a measure of whether the reaction occurs, but also how much work we can get out of it.
Right, exactly. And in this case, we remember that delta G0 is minus NFE0. And so there's that minus sign. So there's our justification that B would be our preferred choice. And so, anyway, students, you have the remainder of this PowerPoint. I'm going to share with the teachers answers to the remaining slides on this PowerPoint. And so I would encourage you to go ahead and do those at a time that's convenient. And then if Lou, if you would allow me maybe just one more couple of minutes, I'd like to have a friend sing a song.
That's fine with me.
Cerium and cesium and lead, plutonium, palladium, lithium, potassium, polonium, and tantalum, magnesium, titanium, tellurium, and cadmium, and calcium, and chromium, and urium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, xynium, nobelium, and argon, and plutonium, radium, uranium, rhodium, and chlorine, carbon, cobalt, copper, tungsten, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
All right.
Thanks,
So
John.
there's the Element song. It's sung by Tom Lair.